Welcome, ladies and gentlemen, to this video lecture. Okay, so in our previous video lectures we discussed and proved the fundamental theorem of calculus, and we notice here it concerns a function little f that is continuous on a closed interval, on a finite closed interval. But very often we work with functions that are defined on the entire real line. So we would like to have a version of the fundamental theorem of calculus for functions little f that are defined on the entire real line. So let us discuss a version of the fundamental theorem that works on the entire real line. So theorem, let f be a function from the real numbers to the real numbers, and let it be continuous. Then for any fixed real number a, we define big F as the integral from a to x of little ft dt, and this is for any x in the real line. Then f is differentiable everywhere, and we know exactly what its derivative is. So the derivative of f of x is equal to little f of x, and this is for all x in the real line. Let me also just write here the domain and the codomain of f. So f maps from the real numbers into the real numbers. Okay, the proof of this we will leave as an exercise. But let us discuss an example that shows exactly how the proof goes. So, example. Let us define a function capital F as follows. F goes from the reals to the reals, from 0 to x t squared sine t squared dt. Show that the derivative of f of x is equal to x squared sine x squared, and this holds for all x in the real line. Okay, so notice here that our function f and our integrand here, they are continuous, or no, let's say our integrand here is continuous on the entire real line. So the idea here to solve this problem and to prove this theorem, the idea is to restrict your view to a smaller interval, a smaller closed interval, to apply the fundamental theorem of calculus, and then to forget that you have restricted. So that is the idea. So let's write out the solution for this function. So for this example, so we want to show that the derivative of big F is equal to x squared sine x squared. So we will do this in two cases. So the first case, case 1, that is when x is bigger than 0. So let x be bigger than 0, and let's just take any b that is bigger than 0. Or let's say fix any number b that is bigger than x. I thought I said 0. I mean bigger than x. Then what do we have? We've got x is an element of the closed interval from 0 to b. Okay, but now we know that the function that sends x to x squared sine x squared, that is continuous on this interval. So we can straight up apply the fundamental theorem of calculus to obtain the derivative of big F. So by the fundamental theorem of calculus, so I'm just going to write FTC, the fundamental theorem of calculus, we obtain that f of x is equal, the derivative of big F of x is exactly the integrand of our integral with our t's replaced with x's. So if you read the fundamental theorem of calculus, that is exactly what it says the derivative is. So this is the easy part. And now notice here, this holds for all. This is true for all positive x's. So for all x positive. And now you see here, to be able to apply the fundamental theorem of calculus, what did we do? We restricted our view to this closed interval from 0 to b. We applied the fundamental theorem of calculus, and then we just forget that we just did that we restricted our view there. So that is what I mean by forgetting that we restrict our view. Okay, let's do the other case. So the case 2, this is when x is less than or equal to 0. And we will do something similar. So fix any a which is less than x. And what we will do is we will restrict our view to the interval from a to 0. So we restrict our view to the interval a to 0. Okay, and now we want to apply the fundamental theorem of calculus. But before we can do that, we must do a little bit of thinking. So f of x is defined as the integral from 0 to x of x squared sine x squared, t dt. But we are working in the case when x is less than or equal to 0. So let's swap these. Let's swap the order of integration. So x to 0, t squared minus t squared sine t squared dt. So if you think about what we're doing, x is over here somewhere, instead of integrating from 0 to x, we are integrating from x to 0, but when we swap the order of our bounds in our integral, the sign changes. Okay. And now, keep in mind, what are we doing? We want to restrict our view to the interval from a to 0. So let's just make a little diagram here. A is over there, x is over here somewhere, and 0 is over there. So let us think about the following integral. A to 0 of t squared sine t squared dt. And let us split this up as follows. So this is equal to the integral from a to x, so from here to there, of t squared sine t squared dt, plus the integral from x to 0, so from x to 0 of t squared sine t squared dt. Okay, let us take this across to the other side and see what happens. So here we've got let us swap. Let's take this term also to the other side. So let us swap everything around, but what do we get? We get minus x to a t squared, no, x to 0, so apologies, t squared sine t squared dt. This is equal to, and now what do we have? We've got integral from a to x t squared sine t squared dt minus our integral from a to 0 t squared sine t squared dt. So all that we did here is we took this term to the other side, this term to the other side. But notice here now, here we've got f of x, because we noticed here that f of x is the integral, or is minus the integral from x to 0, and this is exactly what we have here. So we've got f of x is equal to integral from a to x t squared sine t squared dt minus the integral from a to 0 of t squared sine t squared. Okay, but now notice here we can apply the fundamental theorem of calculus to this term. So, for example, if we define g of x as the integral from a to x of t squared sine t squared dt, and we define g on the interval from a to 0. So notice here now we are restricting our view to this closed interval, and now we apply the fundamental theorem of calculus to this function. So by the FTC, fundamental theorem of calculus, the derivative of g is just equal to x squared sine x squared. But then the derivative of x is equal to the derivative of g, and notice here this is just a constant. So this remaining term, that is just a constant. You see, it nowhere does there occur an x in there. So this term is just a constant, so that is minus 0. So the derivative of big F is just x squared sine x squared. And there we are done. So now we have shown that the derivative of big F is also, in the case when x is less than or equal to 0, is also x squared sine x squared, which was our goal. And what did we do here? We restricted our view. We fixed any number less than x, and we restricted our view to this interval from a to 0. Then what did we do? We manipulated our function big F, and we manipulated it in such a way to end up with f of x equal to this integral minus some constant. And lo and behold, this term is in such a form which allows us to apply the fundamental theorem of calculus. So this function g we define on this interval from a to 0. We apply the fundamental theorem of calculus, and then we just forget that x lived inside of this fixed interval. Okay, and that is it for this example. We'll see you in the next one.